Welcome back to our next lecture. In the last lecture, we briefly introduced the concept set and its notations. We defined set as a well-defined collection of objects in the sense that we can definitely decide whether a given particular object belongs to a given collection or not. We know that the sets are fundamentals in mathematics and understanding their types is also very important. And therefore, today we are continuing our lecture regarding various types of sets. There are several types of sets based on their content, elements, and characteristics or the properties. And accordingly, we have number of types of sets. We are going to discuss each and every types of sets in detail. See, the first one is null set. The term null set is also known as it is empty set or void set, or which is refers to the set that contain no elements. It is typically denoted by a symbol, it is phi, read it as a phi, or empty set symbol. Or even we can put a curly braces without any elements. So this set has no members and it is fundamental concept in the set theory. For example, see, A is the set of all elements of X such that X is a positive number less than 0. So here a set of positive number which is less than 0 would be, of course, it is an empty set because there are no positive number that are less than 0. So this set would be represented by phi or simply a curly braces or bracket in this case. Now let us consider another one. Set A is equal to, or set A is the elements of X such that X is a days in a week with 8 days. We know in a week has only 7 days. It has only 7 days. And the set of days in a week with 8 days is, of course, it is an empty set. 2 points you should keep in mind with regarding to this, a null set. First one, see, the empty set is not equal to the set containing a empty set. The empty set is not equal to the set containing empty set. So the empty set contains no elements, of course you know it, while the set containing one element, that element is empty set itself. So of course the empty set and set containing empty are different. Secondly, see, the empty set is not equal to the set containing the element 0. See here, the empty set phi has no elements, no doubt, while the set containing 0, which means that which contain one element, that is number 0. So phi and the element 0 are different. This distinction is very, very crucial in the set theory, especially to avoid the confusions. So this is all about the null set, where set has containing no elements. Now let us consider another type of set which is known as, it is finite set. A finite set is a set that containing of a finite number of elements. Finite number of elements. A finite number of elements, which means that it contains a definite countable number of elements. For example, see, set A is equal to 1, 2, 3, 4, 5. This is a finite set with 5 elements. These are 1, 2, 3, 4 and 5. Because these numbers are countable in the sense that we can say that it is a finite set. Now let us consider another example. See set B. Set B is equal to 2, 4, 6 up to 50. See, is it a finite set? See, while this set is defined using an ellipsis, that is set of dots, the pattern suggests that it contains the even numbers from 2 to 50. Since this range is finite and countable, we can say that B is also a finite set. Thus, for a set to be considered a finite, we must be clear and specific way to count its elements. And counting the process must eventually stop. Otherwise, it will become infinite. If set goes infinitely, then or indefinitely, then it is considered as an infinite set. So let us consider the third set, that is, infinite set. Infinite set is a set that having an infinite number of elements. Then we can say that it is an infinite set. It is a set that contains an unending, or we can say that it is limitless number of elements. Then we can say that it is an infinite set. See, for example, set A is equal to 1, 2, 3 and is given dots. What do you mean by this particular set? This set includes all the natural numbers starting from 1 and continuing indefinitely. It is an unending, limitless number of elements. Therefore, we can say that this given set, that is set is equal to 1, 2, 3 dots, it is infinite set. Let us consider this set B. Set B is equal to 2, 4, 6 dots. Similar to the previous example, that is set A is equal to 1, 2, 3 dot. See, here also set B is equal to 2, 4, 6 dots. Similar to that, see, this set include all positive even numbers and extends infinitely up to any number. We don't know it. So therefore, it is also an example of an infinite set. Let us consider another example. See set C, which is the all elements of X, such that X is the number of stars in the sky. This set refers to the counts of stars in the sky. Since the number of stars in the sky it's practically limitless, and this set is also considered as an infinite set. Thus, infinite sets are characterized that their elements cannot be counted in a finite manner and set continuous indefinitely. Now let us consider another type of set which is known as equal sets. See, two sets, set A and set B, are said to be equal if all the elements of set A belongs to B and all the elements of B belongs to A. That means two sets A and B are equal if they contain exactly same elements, regardless of the order of elements or repetition within each sets. Let us consider, see, the two sets are equal. We are already said that it is equal only when we have exactly same elements. Let us consider one example. Set A is equal to 1, 2, 3, 4 and set B is equal to 3, 1, 2, 4. See, what is the characteristics of these two sets? See, both sets have the same elements. Though the two sets are different in order, they are equal sets because 1, 2, 3, 4 and 3, 1, 2, 4. The order is changing, but we have a same elements. Let us consider, therefore we can say that this is an equal set. Consider another example. See, set A is equal to A, B, C. Set B is equal to A, C, C, B, 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 B. See, A is repeated thrice and C is repeated twice and B is repeated 4 times. See here, do you think that these two sets are equal sets? See, a set does not change even if one or more elements of the set are repeated. Here what happened? Repetition is happened. In this case, the order and repetition elements does not matter. Both set contain the same elements. Set A, B, C. Set B, A, C, B. Without considering the repetition. Both sets are containing the same unique elements. So they are equal sets. That's why we generally do not repeat any elements while describing a particular set. Now a particular question. See whether the following pairs of sets are equal set or not. Let us consider one example. See, X is the set of letters in the word alloy. Alloy. A-L-L-O-Y. B is the set of letters in the word which is loyal. The question that whether these sets are equal set or not. If you write these sets in a roster form, without considering its repetition, we can write the elements of alloy and loyal without considering the order and repetition. See, the spelling in alloy, without considering the repetition, the spellings are A-L-O-Y. And similarly, the spelling in loyal are C-L-O-Y-A without considering the repetition. So we can write, see, X is the set which is equal to, the elements are A-L-O-Y. Set B is equal to L-O-Y-A. Set B is equal to L-O-Y-A. See, both set contain the same elements. Both set contain the same elements in the sense that A-L-O-Y. The order and repetition of the letters, do not matter while determining the equality of sets. Therefore, in this case, sets X and B are considered as an equal sets. Now let us consider another type, see, equivalent sets. As against the equal set, we have another type which is known as equivalent sets. See, the two sets are considered as equivalent if they have the same number of elements. Even if the elements themselves are different. See how it is different from equal set. See, when both sets are equal, if they containing exactly the same elements. But in the case of an equivalent set, if the number of elements in the given sets are the same. Let us consider one example. See, set A is equal to 1, 2, 3, 4. Set B is equal to B, A, L, 1. In this case, both set have 4 elements. Both set have 4 elements. In the set A, we have 1, 2, 3, 4 and set B, B, A, L, 1. There is a 1-to-1 correspondence between the elements. It means each elements in set A can be paired with a unique elements in the set B. 1 in set A corresponding to the B in set B. 2 in set A corresponding to A in set B. 3 in set A corresponding to L in set B. And 4 in set A corresponding to 1 in set B. Since there exists a 1-to-1 correspondence and both sets have the same number of elements, we can say that set A and set B are equivalent sets. So we have a one-to-one correspondence. Accordingly, we can say that these two sets are considered as an equivalent sets. Now let us consider another type of set which is known as singleton set. A singleton set stands for it is singularity. And a singleton set itself, name itself suggesting that the set containing just one distinct object. It is a set that containing only one element. Let us consider one example, that is set A is equal to 3. See, we have only one element, that is 3. It is a singleton set because it containing only one element, which is the natural number 3. Consider another type of set which is known as subset. A subset is a set which is formed by taking some or all the elements from another set, which is called a superset. So in this case, every element of the subset is also elements of the superset. Let us consider one example. See, set A is equal to 1, 2 and set B is equal to 1, 2, 3, 4. See here, A is a subset of B. The set A is the subset of B because every element in set A, that is every element in set A means 1 and 2 is also element in set B. In mathematical notation, we can write this is as A is the subset of B. Set A is said to be subset of B if every element of A is also an element of B. We can write A is the subset of B if whenever A belongs to set A and then A is also belongs to set B. So it is often convenient to use this symbol, it implies, which this symbol is denoted to show that it means implies. So using this particular symbol, we can write the definition of a subset as, see, A is the subset of B if A belongs to set A implies A is also belongs to set B. Now let us consider another set C. Set C is equal, along with this particular example, A, B and set C, 5 and 6. See here, set C is the subset of B or not? Is it subset of set B or not? See here, C is not a subset of B because none of the elements of set C, that is 5 and 6, are present in B. So it is not part of set B. Therefore, we can say that set C is not a subset of set B. We can write it, that is set C is not belongs to, or not subset of set B. So thus a subset is a set that containing only elements that are found in another set. That set is considered as a superset. And we used to denote, that is A belongs to B, to denote that A is the subset of B, to denote that particular set. Now, it is important to note that the set can be a subset of itself. A set can be a subset of itself, which is also known as it is the reflexive property. It is a reflexive property. It is generally known as it is a reflexive property of the subset relation, which states that any set is a subset of itself. See, symbolically we can write, if A is the set, then A is the subset of A. A is the subset of A. Another important point kept in mind, that empty set, that is phi, is a subset of every set. A phi is the subset of every set. So we defined a empty set as a set, of course, with there is no elements in empty set, there is no elements. It is considered as a subset of every set. So symbolically, if A is a set, then phi is the subset of A. You should be kept in mind. Phi is the subset of A, and a set can be subset of itself. Okay. Now, see, consider one question, that is, we have given the set of phi, set A, which is having the elements of 1 and 3, set B is having the elements of 1, 5, 9, and set C is having the elements of 1, 3, 5, 7, 9. You just want to insert the symbol is subset or not subset between each of the following the pairs. For example, see the first question, whether phi is the subset of or not subset of B. A is the subset of B or not. A is the subset of C or not. And similarly, B is the subset of C or not. So, in the first case, we know that empty set is the subset of each and every set, including set B also. So, therefore, we can say that a phi is the subset of B. Similarly, the second one, set A is subset of B or not. See here, set A 1, 3, set B 1, 5, 9. So, set A is not a subset of set B because there is an element in A that is 3, that is not in set B. So, we can write it is A is not subset of set B. Similarly, the third question, that is set A is a subset of set C or not. Set A, the elements of 1 and 3. Set C, the elements are 1, 3, 5, 7, 9. So here, set A, of course, it is a subset of set C because every element in the set A is also the element of set C. Therefore, we can say that A is the subset of C. A is the subset of C. Similarly, the last question, see whether B is the subset of C or not. We know the elements of B are 1, 5, 9, and the elements also of the C are 1, 3, 5, 7, 9. So here the set B is the subset of C because every element in B is also the elements in C. Therefore, we can say that B is the subset of C. Now, consider the another type of set which is known as proper subset. If every element of set A is also an element of set B and at least one of the element in the set B does not belongs to A, then A is a proper subset of B. See, symbolically, this is denoted as, see, A is the subset B, or we can say that we can read it, A is a proper subset of B. It is a proper subset of B. For example, see, set B is equal to A, B, C. Then the proper subset of B are, there is a possibility that is set A, set B, set C. See, A is the subset of B. B itself is a subset of set B. Set D, which is having the element of C, which is also subset of set B. AB is also subset of set B. BC is also subset of set B. AC is also subset of B. And phi, of course, it is an empty set, is also subset of set B. So B is a superset of all the above sets. And it is important to note that a set is not a proper subset of itself. We are not denoted here in the subset category, that is the set having A, B, C. So set A is not a proper subset of itself, because proper subset implies that there must be at least one element in the superset that is not in the subset. Therefore, a set itself is not considered under proper subset. That is, if B, that means B is A, B, C, which is the subset of itself. But if we include it, that category, that means subset of itself, then what happened? If we include that particular category, then it simply become the subset, not a proper subset. So that's why we are not considered a set itself as a subset under proper subset category. I hope you understood the differences between the concept of subset and proper subset, which are related to inclusion of elements in the set. Let me clarify again. See what are the various differences between set, subset and proper set. In the case of a subset, a set A is considered as a subset of B if every element of A is also element of B. If every element of A is also an element of B, and the symbol generally we are used to denote here, A is the subset of B, that is A is the subset of B. Keep in mind here A is may or may not be equal to B. Therefore we can say that set A can be subset of itself. A set can be subset of itself. But in the case of proper subset, let us consider. See, set A is a proper subset of set B if A is the subset of B and B is not equal to B. A is not equal to B. It means that all the elements of set A are in set B, but B contain at least one more elements. This is the symbol which is used here to denote the proper subset is A subset B, or it can be written as A is proper subset of B, but A is not equal, A is subset of B, but A is not equal to B. So therefore, a set cannot be a proper subset of itself. But a set can be subset of itself in the case of a subset, but a set cannot be proper subset of itself. So I hope you understood the differences between subset and proper set. Now let us consider another type of set which is known as power set. The collection of all subset of a set A is called the power set of A, and which is denoted by PA, which is generally denoted by it is PA. That means it is the power set of A. Thus it is the set of all possible combination of subset of all the possible subset of A including empty set and set A itself. For example, if A is equal to A, the element A, then the subset of A are this set itself, that is A, and also phi. There are power set A is equal to, it is collection of all subsets. So here for the set A, we have the subsets are set A itself, and phi is also the subset of all the sets. Now let us consider if A is equal to two elements, that is A and B, then what are the various possible subsets? A is a possible subset, B is another possible subset, AB is another possible subset because AB is means subset of itself, and phi is also subset of all the sets. So the power set here, it is including all the possible subset, that is A, set B, AB and phi. which are included in the power set. Let us consider if we have three elements in this set, that is set A is equal to A, B, C. Now in this case, see what are the various possible subsets. See, A is the possible subset, B is also possible subset, C is also possible subset, AB is another possible subset, BC, AC and ABC itself is a possible subset, and also phi. So these are the various possible subsets of set A, B, C. We can write the power set A, which is equal to the set of A, B, C, AB, BC, AC, ABC and phi. So this is the power set, which means that it includes all possible subsets of a given set. Now, if A has n number of elements, we are just counted 1, 2, 3. But if A has an n number of elements, then the number of all possible subsets can be found by using very simple formula, that is known as number of elements in the power set, that is NPA. Number of elements in power set A is equal to 2 raised to the power n, 2 raised to the power n, where n is the number of elements. If the first example, in the previous example, we have n was only 1, that means number of elements was only 1. Therefore, NPA, number of elements in the power set A is equal to 2 raised to the power n, which is means n is equal to here only 1 elements, so which is equal to 2 raised to the power 1, which is equal to 2. Similarly, we can say that, that's why we can say that these PA are, 2 elements are set A and phi. Now consider this set B, set A, we having 2 elements, where how to find how many possible number of subsets are there. See, NPA is 2 raised to the power n, which is equal to 2 raised to the power 2, that means 2 square, which is equal to 4. What are the various 4 possible subsets? See, here it is A, B, AB and also phi. Then the third example we were considered, that is set A is equal to ABC. And here the number of elements in the power set A, which is equal to 2 raised to the power n, which is equal to 2 cube, which is equal to 8. It's repeatedly written here. So it is 2 cube, which is equal to 8 elements are there. So here the number of possible elements in the power set A, B, C, AB, BC, AC, ABC, that means set itself and phi. So in this way, we can find the number of elements, that is possible subsets of a given set. Now, let us consider another set which is known as universal set. See, a universal set is a set that contains all the elements under the consideration for a particular discussion or the problem, which is generally denoted by U, and which is generally known as it is universal set. It is a set that has element of all the related sets without any repetition of elements, and every set being discussed is considered a subset of this universal set. For example, we can consider an example. A pack of cards can be a universal set U. See here, the set of diamonds or shades in the context U would be include all individual cards in the ender check. So in the example, let us consider another example, the set of integer that can serve as the universal set U. Here, for the set of even or odd numbers, here U is, encompass all the integer, and set of even and odd numbers are, subsets, possible subsets of the universal set. So here universal set is set of integer that can serve as a universal set. So accordingly, we can have all the even number and odd number will become the subsets of this particular entire universal set. And it is important to note that, the choice of universal set. What will be a universal set is, it's entirely depending upon the context of problem or discussion, under discussion, whatever we are going to consider under a particular moment, which will become under the universal set. Now let us consider the last set, which is known as disjoint sets. See, disjoint sets are also known as, it is mutually exclusive sets. It is known as mutually exclusive sets, and these are the sets that have no elements in common. And here it is key criteria is that they do not share any elements. These two sets will not share any common elements. Thus, if a set are disjoint, then the intersection of these sets is empty set. For example, set A is equal to set P is equal to elements of 1, 2, 3, and set Q is equal to 4, 5, 6. See, these two sets are disjoint sets because there is no repeated common elements which are found in the set P and set Q. That's why there is no common elements in these both sets. We can say that these two sets are mutually exclusive, or these are the disjoint sets. Let us consider another example, the set colors. Colors are included here, red, blue and green. And another set, see, set days, Monday, Tuesday and Wednesday. See here, these two sets are disjoint set. And it is not, these two sets are does not related to each other, because the criteria of these two sets are entirely different. One is color and another one is days. So colors are red, blue and green, but at the same time days are Monday, Tuesday, Wednesday. So these are unrelated sets. So there is no common elements in both these two sets, and accordingly we can say that these are the disjoint sets. So we are going to conclude this lecture here. In this lecture, we are discussed the various types of sets, especially, null sets, finite and infinite sets, equal sets and equivalent sets, subsets, supersets, proper sets and power sets, and finally a universal set and disjoint sets. I hope you understood all these sets very clearly. Go through these sets once again, and in the next lecture we will discuss Venn diagram and the set operations like union, intersection, complement and differences along with its properties. So we will see in the next lecture, and thank you.